So welcome back, everyone. Um, let's continue our course. This is lecture 16. The topic of this lecture is how to extend the predictions we can make about a physical system in quantum mechanics. And to be more precise, we know that the wave function as a function of x, and in general the time-dependent wave function, provides me the probability of observing the particle at configuration x, or at point x, and time t. And in order to get that, all you have to do is to take the square modulus of the wave function. I think at this point, I've discussed this fact many times. Now, but we know from quantum mechanics that, we know from our description in classical mechanics that at least in classical mechanics, there are two equally important pieces of information that concern the dynamics of a particle, that is the position x, which sometimes we refer to as with the letter q, but also the momentum p, which is in classical mechanics related to the q variables by the usual velocity times mass. So far, we have discussed what is the probability of observing a given state of configuration q at time t in quantum mechanics. What we now want to address is, can we say the same for the momentum? How can we predict what is the probability of observing a particle with momentum p in a system? That will sort of close the circle, because we know that momentum and particle and position should sort of be two equally important part of the discussion, right? That's what the phase space is all about, after all. However, the standard quantum mechanical formulation sort of treats momentum and position separately. What do I mean by that? I mean that you have a wave function that describes the probability of finding the particle with a particular position, at a particular position. However, it doesn't tell me anything about the momentum. It doesn't tell me what is the momentum of a particle. I have an uncertainty about the momentum. Let's sort of try to conceptualize on this problem by going back into our discussion of the double well, of the infinite well. In the infinite well, we have, for instance, the ground state wave function that in the notation we used in the last lecture was noted with a 1. In the previous lectures, I was using the notation with 0 here. Doesn't really matter. The notation that starts from 1 is convenient when you want to use even and odd function in a single expression. But what it is, we know that the wave function for the ground state of the system was actually written in the following way, where k1 was actually pi over L and the energy was actually h bar square k1 squared over 2m, right? So as you can see, if you plot this, in my as a function of x, you get a normal cosine. Now, if you want the probability out of this, of course, you have to take the square. Now, the point here is that there is an intrinsic uncertainty here that is referring to the fact that a particle can be found anywhere. Everywhere, the probability is, roughly speaking, is significantly different from zero, and the probability here is significantly different from zero, more or less everywhere. So the typical uncertainty on the position of the particle delta x is of order L, right? On the other hand, from this equation, I know that the kinetic energy has this structure, which we already had in discussion, tells me that the modulus of the momentum is of order, is actually, if I identify this with, if I interpret this as p squared over 2m, then basically I must conclude that p squared is of order h bar squared k1 squared, which is h bar squared pi squared over L squared. And based on this, I'm led to thinking that the typical size of the momentum is order h bar pi over L, okay, in the ground state. We already went through the fact that there is a 0-point energy because I am, because of uncertainty principle, basically, I'm confining the particle to be in a fixed region. The particle is not completely delocalized, as a result of which there has to be some uncertainty in momentum. And the uncertainty in momentum is due to the fact that, you see, I know the modulus of the momentum, but I do not know the sign of the momentum. So if you want, the typical uncertainty in the momentum is twice this modulus, because it could be this or the opposite of it. And in fact, it is not even a discrete value. I don't even know what the momentum is. This is what I basically know is the kinetic energy of the particle, right? And from the kinetic energy of the particle, I can interpret this as the momentum. So I know that the momentum is typically of the order of this quantity. Which basically is telling me that I have an uncertainty on momentum, which is 2h bar over L. So that means that for this particular system, since h bar is h divided by 4, I have delta x, delta p of the order of h half. This is the celebrated Heisenberg uncertainty principle. The more I shrink my uncertainty over position, the larger I make the uncertainty over momentum. In the opposite limit, when I make the uncertainty of the position large because I'm getting a wider and wider box, the kinetic energy gets to 0, and I'm getting, as a matter of fact, lower and lower uncertainty on the momentum. So that's sort of the story, right? So in quantum mechanics, I don't know, I can never know positions and momentum with infinite accuracy. And it turns out that from many experiments, it became clear that this relationship was not something that was concerned only square well, but it was a general feature of quantum mechanical system. And it goes under the name of Heisenberg uncertainty principle. And it's basically something that is always there in quantum mechanics, no matter what. It's the famous fundamental limitation of nature to be determined in terms of position and momentum in a completely closed way. So this is Heisenberg. Uncertainty principle. Now, however, I want to emphasize, even though in classical mechanics, positions and momentum are treated at equal weight, they are given equal importance. In fact, a state in classical mechanics is a collection of position and momentum coordinates. In quantum mechanics, so far, we have only obtained the probability of finding the particle as function of position. And therefore, we are decoupling the theoretical questions in a question about position, and maybe we want to ask now, what is the questions about momentum? What is the probability of finding a particle at given momentum? And I guess this is one of the features in quantum mechanics where you don't, at retrospectively, when we will define the general rules of quantum mechanics, and we discuss about bases of the Hilbert space, and all this will become just a corollary of that very general rules of quantum mechanics. At the moment, we are not sort of looking at the rules and deriving down the application of the rules. We are trying to get to the rules by adding one piece at a time. We had the Schrodinger equation. Now we add another piece of information. And then at some point, we will stop and formalize everything we said in a set of rules that generalize everything that we have done, right? So in this respect, all we want to know is, we want to postulate a way to compute this that is consistent with the idea that this product is always constant, that I can never get this product to be much smaller than h power of 8. Which means, for instance, if I have the wave function position space that is extremely localized with, say, Gaussian with a width typical sigma that is very small, and this describes the probability of finding particle at x, I want the probability to find the particle with momentum p to be correspondingly very large. Basically, the uncertainty on x is sigma. Then, of course, the uncertainty on p must be proportional to 1 over sigma, because you see the uncertainty on p is proportional to h over 2 delta x. So we want something that basically that allows me to compute the probability of finding a particle with a given momentum that respects the fact that it becomes more and more delocalized, the more the particle is localized in position. And vice versa, if we know very accurately the position, the distribution in momentum space, and the probability of finding a system with a given momentum, I want some mathematics to tell me that the corresponding probability in position space must be very broad and therefore very little information there. And the way quantum mechanics encodes this very specific information into its formalism is through the concept of Fourier transformation. So once again, this concept at the moment is postulated. You're not expected to be understanding this as a logical implication of whatever we have done so far. Just that experiments like the Heisenberg principle, and this is a mathematical way to be always consistent with the Heisenberg principle. But later on, I said this just a few minutes ago, but I'm going to stress on this concept. Later on, we will present a formulation of quantum mechanics that is more general than just position, momentum. It just concerns anything that can be measured. And it will contain a set of postulates that define quantum mechanics mechanics. And this would be a specific, special case for one of these postulates. So what I'm trying to say is that at the end, when we will formulate the rules of quantum mechanics, this will come down as one of those rules in a specific case applied to a specific situation. But for the moment, we just, going to say we like the uncertainty principle because experiments sort of find it over and over. And we want the mathematics that is, so to say, consistent with the uncertainty principle. And basically, what this is saying is that the probability of finding the particle time a momentum p time t is given by the square modulus of a new object, which is the equivalent of the wave function in position space, but now it's in momentum space. So this should be confronted with the previous where there was no tilde. The tilde is there to remind me that this is something different from what we were computing before. Yeah, it's a different function. So how does this phi tilde relate to the previous psi function? Well, this is the postulate part of it. It's an integral from minus infinity to plus infinity of dx e to the x dot p h bar times psi of x t. And similarly, I can go from the tilde to the psi tilde to the x by a similar equation, which now involves. Let's do this for one dimension. Oh, no, good. Oops. So what does this equation tell me? That the probability of finding a particle m momentum p at time t is obtained from a function, wave function modulo square, which is called the momentum representation wave function. And the momentum representation wave function is obtained from a normal wave function or position representation wave function. Through a mathematical operation called Fourier transformation. What is a Fourier transformation? You take the function as a function x, you multiply by a phase in which you have an exponent which looks very much like the plane wave contribution as x and p, and then you integrate over all values of x. If you do this integral, you obtain a function, x, the dependence on x vanishes because it's integrated over, and everything that remains is the dependence on p, right? Because that's the parameter in the right-hand side of this equation. And this is why this function is a function of p. And of course, it's also a function of t, because the left-hand side depends on t through this part here. So I'll come in a minute to motivate why this specific mathematical formulation is the one that we need. So if you know the wave function in position representation, say, because you have solved the Schrödinger equation, then you can get the wave function in momentum representation by evaluating this integral. For if you're interested in a specific value of p, say p naught, then you evaluate this integral putting p naught right here in the phase. If you want a different value of p, then you evaluate this integral at a different value of p, say p prime. And so on and so forth. You continue doing this for every single value of p you might be wanting. Now, I emphasize there is a symmetry. We expect that there should be a symmetry between how we treat the momentum and the position information. So this is how you go from position to momentum information. But since we expect the theory to treat momentum and position on equal footing, we need an equation that goes from momentum to position. And this is what it is, and it works exactly the same way. Suppose we are interested in knowing the wave function at the given position x, right? That's the position we want to evaluate the wave function. Well, we take the wave function in momentum space. Suppose we have it already. We apply a phase which has an opposite sign, and we perform the integral over the momentum. There is some minor difference. For instance, let me emphasize that in this integral, there is a 2 pi to the third downstairs, but there's no such a thing in the previous integration over d3x here. There is a phase difference here, negative sign here. But other than that, the two expressions are rather symmetrical. So the first line is called the Fourier transform of the wave function. And the second line is called the inverse Fourier transform, or also Anti-Fourier Transform sometimes called. So basically, it's like taking a train from position to momentum and from momentum to position. So if you take the train from position to momentum and the train to momentum to position, you get back to the very same point. And in fact, if you perform the anti-Fourier transform of the Fourier transform, you go from psi of x to psi of p to back to psi of x. And this 2 pi over 3 here is a numerical factor that enters to make sure precisely that you can get any additional constant in this back and forth loop. So let me just draw it. I have a psi of x, and I use t as a function. So I go through the operation called Fourier transformation. To a function psi tilde of p of t. Sometimes it's called as the Fourier transform of psi. Okay. And I can go back from psi tilde to psi through an operation called inverse Fourier transformation. And for this reason, this is sometimes referred to as the inverse Fourier transform of psi tilde. So what this diagram is telling me is that there are two equivalent representations of the information. I can either have explicit information about the position or explicit information about the momentum. but they are not completely unrelated, because if I have the wave function in position representation, I can have, say, the corresponding information of the wave function and momentum by performing that weird integrals that we call the Fourier transformation. And on the other hand, if I have the information about the momentum, I can reconstruct the information about the position about using that weird integral called the inverse Fourier transformation. So that's the way in which quantum mechanics treats position and momentum in real footing. It's very different from from how classical mechanics does it, because classical mechanics says that the classical state is a collection of position and momentum together, and assumes that you can specify position and momentum at any given level of accuracy. Quantum mechanics, because of the uncertainty principle that sits right here, doesn't allow you to treat the state as a system as a collection of position and momentum bounded, but it does have something that reminds of this equal footing treatment of the two by having two equivalent formulations of the dynamics of the system through a space-dependent formulation, which you express the wave function in position representation, and you get the probability by making the square modulus of this wave function, an equivalent formulation in momentum space, in which you take a wave function momentum representation and the probability from the square modulus of this wave function. And you can go from the one to the other through a well-defined deterministic operation called Fourier transformation. Whether you're able to solve that integral analytically or you need computer codes and subroutines to do that, that's an entirely different question. Most of the time, you have to use computers to do that integral. But in principle, it's there, it's well-defined, it has all the properties that you would like. So why are we postulating this relationship, this circle, through the Fourier transformation? Of course, ultimately, because that's what experiments seems to be liking. However, I can motivate this by saying these particular properties of using Fourier transformation for going from position to momentum respects the uncertainty principle. And I can convince you by doing the following integral. Suppose that I have a wave function and that my wave function is some constant times a Gaussian. Okay? Well, let me, since the wave function will be normalized with the square modulus, let me use a 4 sigma here. Oh, yeah, why not? Why do I want to do that? Because if I want to determine A, it's easier this way because I know that A will be determined by the condition. Okay, now I'm working in one dimension, so I don't have a three-dimensional integral here, just one part. So this will give me A, right? And I would say, in this specific case, I would imagine that A is just 1 over 2 pi sigma to the 1/4, I would say. Likely, yes. Doesn't really matter what value is. The important thing is that you can get it. Right. Now, this is a wave function that is picked around the origin with the size sigma. Suppose we know the wave function, suppose this is the spatial part of the wave function. So we don't have to worry about it. There would be a phase for the time dependency. We don't really care about that. So suppose we restrict this to the special part. Time-dependent part is actually 3. Now, what is the Fourier transform of this? What is the Fourier transform of this? Well, let me apply the definition. The Fourier transform will be the integral into full space of e to the negative x squared 4 sigma and there would be a phase Now, it turns out that this integral can be evaluated analytically. It was evaluated by Gauss. It's a very famous integral. Can be evaluated with the methods of complex analysis, which I cannot sort of digress on here. You can, log on Mathematica or Maple or any computer algebra code and ask it to evaluate. You get the result. And the result is something like e to the p squared, but now I get the sigma square upstairs. So you see what's happening here. This calculation is exact, and it's telling me something quite peculiar, that if I'm having a very sharp distribution, that the Fourier transform of a Gaussian is again a Gaussian. So if I have a very sharp distribution in momentum, for instance, let me draw it a little bit sharper, with characteristic scale sigma, the corresponding distribution will have in momentum space, will have a width 1 over sigma. Because you see here is exponent of minus 2 sigma p squared. Well, the new distribution here will be like the sigma p. I know the 1 over 2 sigma p squared is equal to 2 sigma p, which means to 2 sigma, which means that sigma p is going to be equal to 1 over 4 sigma. 2 sigma. So what I'm trying to say here is that here there's a 2. That if I squeeze my wave function in position representation to make it very big, so I have very little uncertainty on where the particle is, because the distribution, probability distribution is very near about 1 point. The corresponding wave function in momentum space will become very broad. So we have very little information on where the momentum of the particle is, what kind of momentum particle. Conversely, if I squeeze the distribution of momentum, knowing exactly what's the distribution in position space look like, in momentum space look like, well, the result of that will be the fact that my position space wave function will be extremely broad and delocalized. And we have an example of that. If you remember the plane wave. In the plane wave, you can think about the plane wave as a state in which the momentum is completely fixed, p, and the position is completely delocalized. So if we take the Fourier transform of that, we will get something in which so to take the Fourier transform of the plane wave, we will get a function that is extremely big in position space, in momentum space, because it's completely delocalized in position space, right? So Fourier transformation are basically the tool to connect position and a momentum state wave function. So the answer to the question, how do I compute the wave function, the probability momentum space, can be drawn in the following way. This is one possibility. I take my Schrodinger equation in momentum space, which means I solve this equation. I take the Fourier transform of the solution, and then I take the square modulus. Okay, so by these three operations, I can get all information I can possibly get about the momentum. And like I said before, this is not to say that I can get all the information I would like to get, because unlike in classical mechanics, quantum mechanics is setting an untranspassable limit about the amount of information I can simultaneously acquire about momentum and position through the uncertainty principle. So I hope this discussion was not too confusing. Unfortunately, there is not a simple way to put it. I mean, the mathematics behind it is a bit more involved than I could sort of have the luxury to expose to you. So, you know, the problem is whatever I said is correct, but in order to make, very thorough sense on all of this, you will need to spend a couple of months in digging what is Fourier transform more in detail and giving more mathematical foundation for that. At this level of this course, we are keeping this at the level of a tool, a set of recipes that they give you and you can use. To go beyond that, you really need a more advanced course in quantum mechanics. But the essence of it is, in the end of the day, it boils down to what I just told you. Take the Fourier transform if you want to go to position to momentum, and keep it as a rule if you want. Okay, I think it's a good point to stop. Maybe I can say, okay, exercise. Compute the probability of finding a particle momentum p for the ground state of the harmonic oscillator. So in one of the meetings we had live, which are not recording on YouTube, I went through the exercise of solving for the ground state of the harmonic oscillator. The ground state of the harmonic oscillator is the ground state of the following Hamiltonian in one dimension. Now, it turned out that the wave function was a Gaussian and that the coefficients and the weight of the one Gaussian I don't have here at hand. You can work this out or look it up in Wikipedia also. And then you can use this information to compute the Fourier transform and see what it looks like. Okay, so I recommend you to do this exercise. It's a nice way of putting your hands into the theory of Fourier transformation. And as far as we are concerned, we are not going to dig very much deep into that. And we will be mostly concerned as probability in position representation. Momentum representations, however, are used by scientists who are most interested in the scattering problems, because you have a beam of particles impacting a target and being diffused, and the probability of making it to another point of the target depends on your velocity. And for instance, if you're interested in the double well experiment, double slit experiments, that's what you want to do. You want to wave functions in mental representation. As a result of which, at the end of the day, in physics, people are used to use both these wave functions. However, when it comes to biochemistry or biophysics, people are mostly interested in properties as function of space, because you want to know how the electrons are distributed in a molecule, what is the probability of finding electrons near an atom or another, and you want to evolve in time the atoms of the molecule. So as far as us is concerned, we will never have to perform the Fourier transform. But it's important for you to know that there is a specular formulation of quantum mechanics in momentum space. Okay, I think this is it for now. See you next lecture.